Zephyr is a real-time operating system for connected, resource-constrained devices, anything from a sensor node to an automotive ECU. The mental model to take away is layered. Applications on the top, then system services, then the kernel, then drivers, then a hardware abstraction layer, then comes, finally, silicon. Around that core sit three things that make Zephyr distinctive. A developer ecosystem built on West, CMake, Kconfig, and device tree. Broad architecture support spanning ARM, RISC-V, x86, Extensa, and Arc. And a rich connectivity and security stack. This is the piece that trips up every newcomer, so anchor it now. Zephyr is a declarative. You describe what you want, and the build system composes exactly that. Two configuration systems work together. Kconfig describes software, what features and subsystems to enable, and device tree describes hardware, what board, what peripherals, what pins. CMake orchestrates the build. Ninja compiles, and you get firmware out. The slogan to remember: software through Kconfig, hardware through device tree, and everything composed at build time. When something doesn't work in Zephyr, the answer is almost always in one of these two systems. The scheduler is the heart of the real-time behavior. Three things to internalize: it's priority-based, it's preemptive, and lower numbers mean higher priority. The highest priority ready thread always runs, period. Each priority has its own FIFO queue. Three policies are available: cooperative, preemptive, and time-sliced. And equal priority threads can share CPU via time slicing if you enable it. On SMP systems, each CPU has its own run queue with load balancing across cores. That's the model. Determinism through priorities. Zephyr's driver model is what makes the same application portable across vendors. Hardware is declared in device tree. The build system generates static device objects. Drivers implement a standardized API and bind to those objects at build time, and your application accesses everything through type-safe APIs. The phrase to remember: one model, many devices. A GPI call looks the same whether you are on Nordic, NXP, ST, or TI Silicon. Only the device tree changes. Drivers are categorized into bus, peripheral, sensor, storage, and virtual drivers, and they initialize in a defined level from early hardware through application. Zephyr ships a full Bluetooth LE host stack, production grade and certified. The mental model is the standard BLE layering: GAP, GAT, L2 cap, SMP, HCI, etc. HCI is the host controller layer, and this controller can be Zephyr's own link layer protocol or a third-party chip from Nordic, Qualcomm, TI, Infineon, or Silicon Labs. Same host either way. Beyond classic BLE, the stack supports Bluetooth mesh, LE audio via ISO channels, and modern security including LE secure connections. Standards-based, power-efficient, scalable from single sensor to an edge gateway. The networking stack is IPv6 first and built around standard BSD sockets, so application code is portable. The mental model is the classic OSI layering: applications, transport, network, adaptation, link, driver. With two things to notice: First, 6LoWPAN sits as an adaptation layer enabling IPv6 over low-power radios like 802.15.4 and Thread. Second, multi-homing is first class. Ethernet, Wi-Fi, 802.15.4, PPP, and USB can all run simultaneously through one unified stack. Security via TLS, DTLS, and IPsec is built in, and the BSD socket API means the code you write on Linux mostly works here too. Security in Zephyr is layered and based on least privilege level. The key idea is the supervisor versus user space split, enforced by the MPU or MMU. Kernel threads run privileged, user threads run sandboxed, and can only reach kernel resources through validated system calls. Every kernel object has an owner and explicit permissions. Around this core sits secure boot via MCU boot, cryptographic services, and optional integration with TFM or PSA crypto. The phrase to remember: isolation, protection, least privilege. It's not bolted on. The architecture is designed around it. Power management is where Zephyr earns its keep on battery-powered devices. Two ideas to lock in. First, system power states: run, idle, suspend to RAM, suspend to disk, off. Describe the whole SoC. Second, device runtime PM. Drivers automatically suspend and resume individual peripherals when idle, reference counted, transparent to the application. These two work together. The system PM policy decides the SoC state based on what devices are active and what wake-up sources are armed. Tickless idle plus runtime PM plus careful wake-up source configuration is how you get battery life measured in years. Zephyr and Linux are not competitors. They're complementary tools for different problems. Zephyr is real-time, deterministic, kilobytes of footprint, sub-second boot, microamps of power. Linux is general-purpose, feature-rich, megabytes of footprint, complex applications, and UI. The decision heuristic is simple. Complex applications, rich UI, or heavy networking stacks equals Linux. Ultra-low power, fast boot, hard real-time equals Zephyr. Most product portfolios end up with both, and Zephyr increasingly handles the MCU side of a system whose application processor runs Linux. This section drives home the portability story. Same Zephyr codebase, same APIs, same build system, same tools, running on RISC-V or ARM, on a tiny Cortex M0 or a multi-core Cortex-A. Architecture support is broad on both sides. Vendor ecosystems are deep. The kernel porting layer keeps the architecture-specific code small. The takeaway: choosing Zephyr doesn't lock you into a silicon vendor or even an instruction set. You can move between architectures with a board change and a rebuild. Testing and CI infrastructure makes Zephyr production credible rather than just a hobbyist RTOS. The orchestrator is Twister. It discovers tests, builds them, runs them on native simulators and on QEMU, on local boards, and on remote hardware in the Loop Labs, and reports results. The unit test framework is Z-Test. Together, they enable continuous integration that exercises the entire matrix of boards, architectures, and configuration on every commit. The mental model: tests run everywhere automatically on every change. That's how a project of this scale stays trustworthy. Observability is built into Zephyr rather than bolted on. The architecture is a pipeline. Applications and subsystems emit log messages through macros. Those go into a memory buffer. A logger thread dispatches to one or more backends, UART, RTT, shell, network, etc. Levels and filtering work both at compile time and at runtime, which matters enormously for production code. Beyond logging, the same subsystem hooks into tracing tools like SystemView and into debuggers via OpenVCD and GDB. The slogan, see more, find faster, fix smarter. And crucially, with low overhead, you can leave it enabled in production. Sensors are everywhere in embedded, so Zephyr provides a unified API for them. One API, any sensor, any bus. The mental model has 3 access patterns. Polling for simple cases, triggered callback for interrupt-driven sensors, and FIFO streaming for high data rate. Channels like accelerometer, gyroscope, temperature, and so on are standardized, and the sensor itself is configured declaratively in device tree. The newer RTOS integration enables async zero-copy reads for high-bandwidth use cases. The win is the same as the driver model: portable application code across sensor vendors. Modularity with West Manifest is how Zephyr scales beyond a single repository. West is the meta tool. Manifest file West YAML describes which repositories at which revisions make up your workspace. Vendor health, optional features, your own application, third-party libraries, all kept as separate modules and composed at workspace level. Benefit is reproducibility. Pin every revision, share the manifest, and anyone can recreate an identical build years later. This is also how vendors keep proprietary code separate from open source code. Zephyr is composable. You assemble exactly the system you need, no more. Finally, the part that matters for products with multi-year life cycles. Zephyr releases roughly every 4 months, and selected releases are designated long-term support, 3+ years of security fixes and critical backports. Regular releases give you new features and a shorter support window. LTS releases give you stability for production and certification. The depreciation policy is disciplined. APIs are depreciated at least one full release before removal. So the takeaway is Zephyr is built for real world, where products ship and then live for years. Plan today, ship tomorrow, and supported for years. Thank you.